Hey, welcome back to Abstract Algebra. In this lecture, I want to tell you a little bit about how we can put into a formal framework in our work in polynomial rings. I think probably one of the oldest problems that you ever saw in algebra. So it's called zeros of polynomials. So let's just start. Here I've got kind of a motivational example here for us. Um, I think probably, maybe not in your first algebra class, because there things tended to be done linearly. You were getting used to just manipulating things in equations, but maybe in your Algebra 2 class in high school, as we used to call it, one of the very first problems that you ever were introduced to in algebra was something like the following. Somebody hands you some polynomial. Here I've got a polynomial, it's a quadratic polynomial, x squared minus 7x plus 12. And you were asked to find all the zeros for it, right? What does that mean? You were asked to solve the equation f of x equals 0. How did you do it? How did you solve that equation? Well, I think you did something like this. You probably took your f of x and factored it. That thing factors into x minus 3 times x minus 4. And then I see the screen has frozen already. Let's see if I can unfreeze it. Took your polynomial, there you go, and factored it into x minus 3 times x minus 4. And then you said, well, if I want that polynomial to equal 0, you set that equal to 0. And then using the zero product rule in the real numbers, the fact that the real numbers have no zero divisors, or the rational numbers have no zero divisors, you were able to say, well, if the product of x minus 3 and x minus 4 is equal to 0, then either x minus 3 is 0 or x minus 4 is 0. And then from there, you can see the two solutions are either x is 3 or x is 4. Good. I want to do the same thing here. It's just that we need to be a little bit more formal because why? I want to kind of get at that same spirit, finding the zeros of that polynomial, but we have to be a little bit careful. It's my warning down here, because up here I'm kind of writing a whole bunch of stuff that doesn't make sense with respect to our definitions. I can't write things like x squared minus 7x plus 12 is equal to 0 because, well, x squared minus 7x plus 12 is a degree 2 polynomial with 3 non-zero coefficients. The 0 polynomial doesn't have a degree and all of its coefficients are zeros. So this equality, it can't mean what we mean by equality of polynomials. Likewise, I can't write x equals 3. X is a degree 1 polynomial with a 1 non-zero term. 3 is a non-zero constant polynomial. It has degree 0. They can't be the same polynomial. So we have to avoid this in our mathematics. We don't really worry about it in high school and middle school and even in calculus, but we don't really want to be writing down sometimes, well, sometimes I mean this is a quadratic polynomial, sometimes I mean it's the 0 polynomial. That's not a good foundation. Those polynomials aren't the same. So we need some kind of formal way to work around this, all right? So this is how we're going to do it. As sort of a preliminary definition, first of all, if you take some field, I'm going to call it E, then a subset of it, I hope this feels like a natural definition, a subset of E is called a subfield if it's itself a field under the same operations, all right? And we're going to use the same kind of notation we use for subgroups, subrings. We'll just write that less than or equal to sign. So we know that it's a subfield in context if both F and E are fields, all right? And in this business, we usually kind of start with F and make E. I'll say F is a subfield of E. It's perfectly fine. I will also say that E is an extension field of F, right? So those mean kind of the same things. And as usual here, maybe as you're watching this video, you want to make some flashcards so I can turn technical terms into our technical term color blue. All right, so there's two technical terms, subfield and extension field. They're just synonyms. Here's an example. Q is a subfield of R, or if you prefer, R is an extension of Q, because Q is a subset of the real numbers that is a field under the same operations of addition and multiplication. Likewise, R is a subfield of C, or if you prefer, C is an extension field of R. All right. So now here's how we're going to get at this notion of 0. So first of all, if you take some extension field of a field F, so E is some extension field of a field F, and you choose an element alpha in E, all right? Then I'm going to define a function, which I'm denoting by phi sub alpha, because it depends on alpha, and it's going to take a polynomial over F and produce an element of E. And here's how the formula works. Phi sub alpha of, I just wrote the polynomial out in terms of its coefficients. So these little a sub i's, I can write it here. I'll write it off to the left. The little a sub i's are all elements of F. Okay, so phi of this polynomial is, well, I basically just replace the indeterminate with alpha everywhere. So I'm kind of substituting in alpha for x. And this makes sense because if E is an extension field of F, then it makes sense to multiply elements of E and F because every element of F is also an element of E. So these products are happening in the field E. The powers of alpha are happening in the field E. The addition is happening in the field E. So when you're all done, you're going to get some element of E. All right, so we call this map the evaluation at alpha map. It's just literally plug in alpha for x. And if E is an extension field of F, then all of that arithmetic makes sense and you get an element of E. Okay, for some simpler notation, if we shorthand note the polynomial by f of x, then I'm going to write phi alpha of f as just f of alpha. And it feels right because we're just sort of substituting the variable, the field element alpha for our indeterminate x. And when we do that, we'll always produce an element of E. Okay, E might equal F, but it could be bigger. Let's look at some examples. I've got our polynomial up here, x squared minus 7x plus 12, and I'm evaluating it at 3. 3 is a rational number. This is a polynomial over the rational numbers, so it makes sense. I'm just replacing the variable with 3 everywhere, and if you compute this number out in the field of rational numbers, you get 0. 9 minus 21 plus 12 is 0. But I can take elements of fields that contain the rationals. The square root of 2 is not a rational number, it's a real number. The real numbers are an extension field of the rational numbers, and so I can plug the square root of 2 into a polynomial with rational coefficients. All right, so this time if I do it, notice that I don't get a rational number out, but nobody promised me I would. I get a real number. In general, when you evaluate phi alpha at some polynomial over f, you get an element of E, the field that alpha comes from, as long as E is an extension of f. Okay? Here's a little exercise I'm going to leave for you. I'm not going to prove it in this lecture. We can talk about it in class if you want to. But for every alpha in E, phi sub alpha is a ring homomorphism. It's designed to be by the way we multiply and add polynomials. But I'm going to leave that as an exercise to you, that this map, phi sub alpha, is a ring homomorphism. So you can call it the evaluation homomorphism if you want to. It plays a very important role in what we're about to do. In fact, its first important role is it's going to give us a way of getting around this, I don't want to write x equals 3 sometimes, and sometimes I mean x is not equal to 3. So here's how we're going to define what I mean by a zero of a polynomial. A zero, or you might have in your algebra classes, these things are also called roots, but I prefer the terminology zero. Okay, so what do I mean by a zero of a polynomial? Let me highlight it in your, I'm going to make a flashcard color here while we're talking. A zero for a polynomial is an element alpha in an extension field of f, f being the coefficient field where your polynomial comes from. All right. Alpha is a zero for it if f is in the kernel of phi sub alpha. So it's kind of interesting. I'm kind of turning the table around a little bit, and I'm saying that an element is a zero for a polynomial if that polynomial is in the kernel of the evaluation at that element. Takes a little bit of getting used to, but one of the benefits of it is that everything we know about ideals and homomorphisms kind of comes into play as our tools when we think about stuff like this. Okay, so written it out in our new notation, I'm just saying alpha is a zero for this polynomial if when you plug alpha in, you get 0. And now this makes sense because the left-hand side of this equation is an element of E. The right-hand side of this equation is an element of E. And it's not nonsense to say two elements of E are the same. Cool. So if you look back at our example, we proved above, you can rewind the video, that 3 is a 0 for this polynomial, because when we evaluated it at 3, we got 0. The square root of 2 wasn't a 0 for it. When we evaluated f at the square root of 2, we got a non-zero real number. Okay? I'll let you check some exercises here just to sort of sink in the notation. The square root of 2 is a 0 for the polynomial x squared minus 2 over q. The complex number I, here I really mean the complex number I, the square root of -1, it's a 0 for the real polynomial x squared plus 1 over q. Okay, cool. So here's a big theorem, our first theorem of the lecture. That if you take a polynomial over f and its degree is at least 2, okay, so it's quadratic or higher, and it's irreducible over f, then it can't have any zeros in f, right? So if you take a polynomial that's got degree at least 2 and it's irreducible over your coefficient field, then it cannot have any zeros in that coefficient field, okay? And I'm going to prove this by contrapositive. I'm going to prove this by contrapositive. Should I write that down? Contrapositive. You know what that means. It means I'm going to assume that f has a 0. I'm going to assume the negation of the conclusion and then try to prove to you that f must be reducible. Okay, if I can show you that if it has a 0, it's reducible, then this theorem follows by contrapositive. So suppose that alpha in f is some 0 for my polynomial. My polynomial has degree at least 2. Okay, so if alpha belongs to the field f, then the polynomial x minus alpha is also a polynomial over f, the linear polynomial x minus alpha. So then we break out the division algorithm. Divide f by x minus alpha. You get a quotient and you get a remainder, okay? And that remainder, the division algorithm says, is either 0 or its degree is less than the degree of what we divided by. The degree of what we divided by is 1. So in either case, this remainder is a constant polynomial. It's either the 0 polynomial or its degree is 0. So it's a constant polynomial. It's an element of the field f, which we just identify with the constant polynomials. Okay, so now if you take this equation, f is equal to x minus alpha times q plus r, and we evaluate it at alpha, well, phi sub alpha is a ring homomorphism. You guys are going to prove it. So when you take phi sub alpha of this right-hand side, you can push phi sub alpha through the product and the sums because it's a ring homomorphism. Okay, we said that alpha is a 0 for f. So f of alpha, phi sub alpha of f is equal to 0. And then on the right-hand side, I'm just doing it. The polynomial x minus alpha, when you evaluate that at alpha, you get alpha minus alpha times q of alpha. I don't really care what it is because it's 0 times it, plus this r of alpha. So we learn that r of alpha is 0, but r is a constant polynomial, right? When you evaluate a constant polynomial at something, you get the polynomial back. It's by the definition of phi sub alpha. Constant polynomials don't have anywhere to plug in and for x, right? So what have we proved? We've proved that r is equal to 0. This constant polynomial r is equal to 0. Well, what does that mean? That means that f is actually x minus alpha times q. The remainder is 0. Or in our language, x minus alpha divides f. All right, but we said that f has degree at least 2. And if you take the degree of this equation using our theorem about how degrees add, you'd get the degree of x minus alpha, that's 1, plus whatever the degree of q is. Well, the degree of q is some non-negative number. You're adding it to 1 and getting something that's at least 2. It must be at least 1. Yeah. So q is not a constant polynomial. Its degree is at least 1. So we've written f as a product of two polynomials, both of which have positive degree. So f is reducible. And theorem 1 follows by contrapositive. All right. Stop the video. Soak it in. I'm going to keep going. The converse of that theorem is false, unfortunately. The theorem says that if you're irreducible, you have no zeros. But it's not true that if you have no zeros, you're irreducible. I've got just a quick example for you here. Here's a 4th degree polynomial over q. It's clearly reducible. You can stop the video and check my math, but that fourth degree polynomial factors over Q into those two quadratics. But that fourth degree polynomial doesn't have any zeros in Q. I'm being a little bit fast and loose here, but the zeros of that polynomial in the real numbers are plus and minus the square root of 2 and plus or minus the square root of 3. None of those numbers are rational numbers, all right? So just because you don't have any zeros doesn't mean that you're irreducible. It's more complicated than that. But we can rescue something. We can rescue something. Our second theorem, I guess I should call it Theorem 2, but I want to call it by its street name, the degree 2 or 3 theorem. The degree 2 or 3 theorem says that if your polynomial's degree isn't more than 3, if it's 2 or 3 more precisely, then not having any zeros is equivalent to being irreducible. All right, I mentioned before in class that it's hard to show a polynomial as irreducible in general, and this is kind of saying, well, if its degree is 2 or 3, it's equivalent to showing it has no zeros. So let's try to understand the proof of this. All right, so here's the statement. If you have a polynomial f over this field f, and its degree is either 2 or 3, then it's irreducible if and only if it has no zeros. Okay, that's what the theorem says. We don't have to prove both directions of this because by theorem 1, if f is irreducible, it has no zeros. It doesn't depend on the degree. So we can just use theorem 1 to prove that. So we need the converse. We have to assume, we have to prove that if f has no zeros, then it's irreducible. And I'm going to do it by contrapositive. I'm going to show you that if f is reducible, that it actually has to have a zero. Okay. So I'm going to show you that if you have a polynomial that's reducible, its degree is 2 or 3, it has to have a 0. So let's assume that it's reducible. So it factors. It factors into two polynomials g times h. They're in f of x. I didn't write it, but I should write it somewhere. So here both g and f have the same kind of coefficients that f does, or sorry, G and H, pardon me, have the same kind of coefficients that f does, and neither one of them are constants. Their degrees are positive. So I'm supposing that f is reducible over f. Okay, and then I take degrees. Take the degree of both sides of this. The degree of f is 2 or 3, and the degree of a product is the sum of the degrees. So here I have two positive integers, degree of g and degree of h, and they're adding up to something that's at least 2 or 3. Well, it has to be the case that one of them has to be 1 and the other one has to be 2. Well, excuse me, if the degree of f is 2, both these numbers have to be 1. 1 plus 1 is the only way you can get 2 by summing positive integers. Okay, if the degree of f is 3, then one of these numbers is a 1 and one of them is a 2. I don't know which one it is, but without loss of generality, I'm going to say the degree of g is 1. Okay, it has to be in both cases. So g is a linear polynomial. G looks like some ax plus b, where a and b are in my field f. A is not 0. All right, so let's just let alpha be the opposite of a inverse times b. Okay, you know what I'm doing here. I'm just letting alpha be the opposite of a inverse times b. You can check, stop the video, g of alpha is 0. G of alpha is the 0 polynomial, and therefore f of alpha is 0, because f of alpha, because evaluation is a homomorphism, it's g of alpha times h of alpha, and 0 times h of alpha is 0. All right? So by assuming that f was reducible, we were able to produce a 0 for it in our field. Cool. So that's kind of, in this course, it's really the only tool. But again, the problem of showing that a given polynomial is irreducible over a field can be quite challenging. Here I can finally prove rigorously, using that degree 2 or 3 theorem, that x squared minus 2 is irreducible over q, because the zeros of it are the square root of 2 and the opposite of the square root of 2, and you probably proved in Math 240 that neither one of those numbers is rational. X squared plus 1 is irreducible over q by the degree 2 or 3 theorem. Its two zeros are plus and minus I. Neither one of those things are rational numbers. In fact, plus or minus I are not even real numbers. So the polynomial x squared plus 1 is irreducible over the real numbers as well. Okay, so now we're at a point where I can kind of state the final goal, the final kind of mathematical fact I want to show you guys in this class. I want to show you that given a polynomial over a field, that we can construct an extension field of f. We can find some field that's bigger than or equal to f, and it will be guaranteed to have a 0 for that polynomial. Okay, this result, if you, I'll tell you the name. Well, I'll tell you right now. It's called Chronicler's theorem. Chronicler. Shouldn't have done it. Chronicler's theorem is that given a polynomial f over a field, you can always construct an extension and find a 0 for your polynomial in it. So I'm interested in applying that to polynomials like x squared minus 2. Yeah, I'd like to construct an extension field of q that has a 0 for that polynomial in it. It's got the square root of 2. And the question is, well, do we have to take, we know R is such a field. Does it have to be as big as R? I'd like to construct an extension of R that contains a 0 of x squared plus 1. I know the complex numbers is such an extension. Does it have to be that big? So that's our main goal. We're not going to accomplish it in this lecture. I'm going to end this lecture just by saying that when we want to accomplish this goal, we might as well assume that f is an irreducible polynomial. Chronicler's theorem doesn't contain it in the statement, but if f isn't irreducible, then it factors into a product of irreducible polynomials, yeah, each one over f. And if you could find a 0 for one of those irreducible factors, then you found a 0 for f, right? In the same way, because when evaluation is a homomorphism, if you find some number to some field element that evaluates at one of these factors and gives 0, well, then that 0 is going to get multiplied by the other ones evaluated. So f of alpha is going to be 0 for that same alpha. All right, so we will accomplish this main goal in the next lecture. Thanks for listening.